All right, we'll get started now. Thank you, folks. So good evening. Welcome to Discover Pinterest. And it's great to see many friends, folks that have been to these events before, and many new friends. And at Pinterest, we host a Discovery event roughly about every 3 or 4 months. We talk about different topics in technology. We engage the community and have a few laughs and get to know each other. So tonight, we're going to talk about cloud engineering. My name is Raj, and I'm part of the cloud engineering team. And we have a great lineup of speakers to start the conversation, share some thoughts with you today. Nori Heikkinen from Google is going to talk about bridge over troubled servers. Great topic. Bogang from Pinterest Cloud Engineering is going to talk about how we do software deployments at Pinterest at scale. Then we'll get into a little bit more details about how we do stateful database management in the public cloud. At least for me, it's quite a feat that we manage that. And then I'll end some thoughts with some of the learnings that we felt having scaled Pinterest on the public cloud. Sound good? All right. So next speaker is Nori, and she comes from Google. She's part of the traffic engineering Essary team, and she's quite a kick, and she has some great thoughts about how Google has scaled the Essary function there, and some great stories. So welcome, Nori.
All right, testing. Cool. Hey guys, my name is Nori. Guys and girls and everything in between. So I chose this corny name because I just wanted to express what Essary does for production, broadly writ. So a little bit about me to start. My name is Nori, as Raj said. I've been at Google for about 10 years and a site reliability engineer for 8 of those. And all of those have been on Traffic Essary, which is a team that maintains the front-end infrastructure layer, most things in between when a user types www.google.com into the browser and when an application front-end serves that request. So it's a pretty fun team. When I first joined the team, I was talking with some friends, or soon-to-be friends and colleagues, and they had a big graph behind their head. And I kept looking at it. I'm like, what could that possibly be? And the y-axis had all these numbers with tons of zeros on them. And finally, I realized that was queries per second. And I sort of stopped in the middle of my sandwich or whatever I was snacking on. And I was like, that's QPS. And they all started laughing. They're like, welcome to the big leagues. So it's been a fun team to be on. And having been on it for the last 8 years, I've watched that y-axis get even bigger. And then another fun thing, I do mean fun, was about 1.5 years ago, I took 1 month and served as part of the tech surge, helping to shore up healthcare.gov when the website launched and then needed some help. So that was a really fun time to sort of take everything I've been taught about sort of the gospel of SRE and then step outside of Google and get a chance to see what truly happens when you don't apply any of that. You know the story on that one. Anyhow, so enough about me. I'm going to talk a little bit about how SRE came to be, and then I'm going to move on to some ways in which I feel like the role can be misunderstood or misapplied. I'm not going to spend too much time on the definition, because I figure most people in the audience are familiar with site reliability engineering, but we'll start with some history. Some ancient history. So you know the story. It's 1999, and 2 guys registered the domain name google.com and run off to Burning Man, as you do. And things thrive, and people seem to like this, and the search engine starts to get more traffic. And that year, So the first couple people start to begin to write some Python automation. This is mostly at the outset focused around sort of job control and machine management and stuff like this. But it's the first sort of incursions into the production scheme. Also that year, we have some couple early hires at Google who are hired specifically to manage infrastructure layers. And at Google in 1999, that meant NetScaler load balancers, that meant DNS, that meant routers, that meant kernels, things like that. But these are also the first couple hires who are specifically doing just that. Next year, 2000, Google hires a couple of people to run the crawl, the web search crawl. This is now a whole crawl and indexing Essary team. These were the first couple of people dedicated to do that. And that was sort of the birth of production team, as we call it. That's our IRC channel. So production team, how did it get started? Originally, they wrote some monitoring, they had a website, they wanted to know if it was up. It's a good philosophy. Not something they did at healthcare.gov, by the way. I kid you not, they had CNN on the wall, and that's how they knew when it was down. So Google had monitoring, and originally the pages, when this monitoring would alert, would go to everybody, all handful of engineers, probably all several dozen. And this was fine because there were few enough people that there's always someone willing to respond to it. But very quickly they noticed that it was the same subset of people who were always responding to the pages. And the people who got the pages but didn't respond to them were really annoyed to get the pages because they were interrupted from their zone of coding and from being able to fit the entire index of the web in memory in one machine or whatever they were doing. So they started to specialize, and a couple of people who were responding to the pages sort of gravitated towards this production team role, and they also pulled in a few people from the systems operations group we call SysOps. And one of the really nice things, this initial sort of hybrid of where the hires came from into prod team, was that you got some instant diversity. You got people with a software engineering focus, and you also got people with a more sort of systems and operational focus in one team explicitly, both doing that kind of work. And that's something we've continued to focus on and to hire for very explicitly since then. So there's also another belief that was enshrined in production team that's continued to happen to today, and I'll get into more of this later. It's that Essary is not an ops team. Urs, who's one of our VPs of Essary, has always said from day one and continues to say, why would you hire a human to do something that a little shell script would do? Why do you want to hire a human to just push buttons, to respond to pages blindly? Surely we're hiring software engineers. Surely they have better ideas about how to automate this stuff, what we should be doing. And so that was enshrined in production team from the beginning and has continued to persist within the culture of Essary, which I think is one of our strengths. In 2003, we formed an ads Essary team to manage specifically the AdWords and AdSense, and that was distinct from production team. In 2004, Gmail spun up an Essary team, and the list goes on. I was going to try to figure out how to have like tons of little logos of different Essary teams all over the slide, and then I realized it would eventually become just black with many, many teams. These days, we're a 1,400-person org over 18 locations. We've grown substantially from the original production team, as you can see. There's two major types of Essary teams at Google these days. There's an infrastructure Essary team. That includes traffic Essary team, what my team does. That includes things like our storage layers that all Google services can use. That includes Borg, our job management system. And there are Essary teams for all these layers of infrastructure. And there's also product Essary teams. This is things like web search, the original one. Production team sort of split off into what became traffic Essary and search. And I like that sort of little original egg cleanly illustrates you have one part that's very infrastructure and traffic and one part that's more product-y in search. ads, Gmail, as I said, basically any major Google product you can think of these days, chances are there's an Essary team associated with it. So Ben Traynor, also in Essary VP, he says that Essary cares about a system's availability, latency, performance, efficiency, monitoring, change management, emergency response, and capacity planning. It's a lot. Basically, one of the things I read about Essary that someone said preparing for this talk is providing a comfortable, smoke-free environment for production since 1999. Things like that. We keep it running. We automate things. We do it in style. You guys are familiar with the role. So that sounds great, right? Essaries magically keep things running. That's definitely what they thought at healthcare.gov. I imagine the conversation went like this. We've got a problem. Do you know anybody who keeps websites running? I don't know. Do you? And on down the line, they found an Essary, and they called us in. So great. So that sounds like a cool role. We keep your website running. So if I describe that to, suppose, the CEO of a company who's got a website with, shall we say, reliability issues, they'd be all, where can I get me some? I want some Essary. Do I just like sprinkle Essary on it and my website will stay up? Not exactly. I mean, it's sort of what happens, but there's a couple of ways that idea can get you into trouble. And these are the things I've been thinking about recently with sort of misunderstandings of the role or misapplications of Essary and some common pitfalls that I want to talk about next. So the most common way in which I think the role of Essary is misunderstood is that it's not the same thing as a purely operational role. Yes, we do carry pagers. Yes, my pager looked like that for many, many years. It was actually Indiglo, and it had a Tetris on it, which was great because then in meetings, I could be like, oh, I'm definitely getting paged. But it was a brick. It was terrible. Now I actually carry 2 phones. But we effectively carry pagers, right? We are on the receiving end of issues in production. What this means, though, is the way I like to describe my job is we first fix things when they break, but then we make sure the same problem never happens again. And that's the real distinction. So the fix things when they break part. This is absolutely not to deny the real operational component of site reliability. We have on-call rotations. We have teams of about 8 to 10 engineers. We think that 8 is about a good minimum because that way you're not having on-call shifts too frequently to get burned out. We think 10 is roughly speaking, a nice maximum because that way you don't go too long in between on-call shifts in order to lose context on production. My team does 12-hour shifts, either 4 days in a row or 3 days in a row, and we have a counterpart in London, which is really, really nice because that way you don't have to get woken up in what is actually the middle of your night. If you're getting woken up in the middle of the night, you're probably actually going to do more damage to the system than any response you would take that you would hope would help. I have examples of that, most notably Belgium several years ago, 1:30 a.m. Don't ask. So we have geographically distinct other halves, and they're true sister teams. So yes, we first respond quickly. The page goes off, we figure what happened, we mitigate. Great. But an aspect of this that I think is also important to note, even within the fact that this is an operational aspect to the job, is that we write our own monitoring. And this is important. You tell people about the role often. What do you do? The cocktail party spiel. Oh, I keep Google running. If their eyes don't immediately glaze over, I go into a little more detail. And then the usual thought is, oh, is there sort of a template of generic production badness that is applied to every system you run, and when some metrics cross various thresholds, you get paged, right? And you have no control over that. Well, no. Our job as Essary is to understand the systems that we manage. And this includes understanding them well enough in order to have a sense of what are those metrics? Are they different for your system versus my system? Should we be using white box monitoring to alert ourselves of impending doom in a way that we know is definitely going to take down production if not acted upon? Should we instead, or maybe in addition to that, be using black box monitoring, sort of full stack probes, and what are the appropriate thresholds for any of that? Very frequently, the actions we'll take as part of postmortems, examining what went wrong, why it went wrong, in the Etsy style, a truly blameless way, include such things as fix the monitoring. We should turn this alert threshold up. We should turn it down. This page is spammy. This one is not giving us enough signal. We're constantly refining this, and this involves a real understanding of the systems we run in order to do this. So already you can see there's not, even though in this operational component, there's not a true sort of pager monkey mentality. And the second half of this, of my fun little one-liner job description, is to prevent that same problem from ever occurring again. This is where I think the value of Essary really starts to tell. Essaries are engineers. That's what the E stands for. If you didn't want to hire engineers, you could have saved some money. But you hired a bunch of engineers. So why don't you let them understand the system and take what they have learned and really feed it back into the system design? I've seen so many good examples of this, of a problem occurs in production, Essaries will respond to it initially first, mitigate it, eventually fix the problem. Very often this ends up being, even the fixing the problem, the root cause part, is a partnership with the development team working together. And at that point, you have a true understanding of what went wrong. Maybe it was simply a bug in the code, but why was the system vulnerable to that bug showing up in that way and actually taking out Iowa or whatever? That's a problem. So if you can design, if you can use the knowledge you've learned from that to feed back into the way the system is set up, to be less vulnerable to cascading failures, be better about load shedding, whatever you've just discovered, let's fix that. And I think that is the sort of thing that, because it's the Essary job, because it's our mandate, we have the time and we have the luxury to sit around and understand this and really feed it back, as I keep saying, into the system design. Whereas the development partners are often more focused on what's next, in our feature list, in our milestone list, and working together, you can really get a better system. Water break. So another problem with the mentality of Essary as magic fairy dust, which is my favorite new phrase, it's a temptation to add more and more Essary for each new thing. Once you've got a proven model where Essary is working really well for you, it's very tempting to say, our traffic is increasing, let's just keep adding more of the thing that supports it. It seems logical. However, this doesn't work for forever. For one, it removes the opportunity to standardize. If you keep sort of growing and bifurcating and exponentially growing your number of Essary teams as well as your number of Essaries, you lose out on the knowledge that each Essary team has gained. It's harder for different teams to be communicating effectively. If you throw more Essaries at the problem, you attenuate the benefit of one team having learned a bunch of lessons from this production experience. The other way is it's just totally organizationally unsustainable. If you extrapolate out your rate of growth, if you've so far been just throwing more and more and more Essary at the problem, you're going to end up with an organization in the tens of thousands of Essaries. And at that point, what does it really mean? Instead, you should be striving for sublinear growth of the teams. Instead of continuing to grow and split, a mature Essary organization will be focusing on similarities of the products they're asked to manage instead of all the differences. Focusing on the differences leads you to the mentality where you end up with tons of different little Essary teams all doing their own thing and not learning from each other. Focusing on similarities gives you the opportunity to say, sure, well, those systems all look pretty similar if you squint. We'll take them on, and over time, First of all, you have the benefit of, if they look similar, if one breaks, you have information from your knowledge about the other system in order to help to inform your research into the breakage of the other one. But also, going back to my earlier point about operational experience feeding back into system design, this is where Essary has the opportunity to begin helping these systems converge. Ideally, if you inherit 4 systems that all sort of do the same thing, over time you can start to ask questions of why do we have 4 systems? Should we instead have 2? Should we maybe rocket science have 1? And to start to help and drive those convergences. So that's my summary of Essary. This is our logo with sharks with laser beams. How we came to be, what the role looks like at Google today, and why it's not really helpful or organizationally useful, I think, to think of the role as magic fairy dust. I hope it gives a glimpse of why it's important to understand and partner with and create space for an empowered Essary organization to emerge, because at the end of the day, you can't scale without it. And that's it. Come find me after for questions.
Thanks, Nori. Hi, everyone. Good morning. Good evening. Thanks for coming. My name is Bao Gang. Tonight, I'm going to talk about the deploy system we created at Pinterest and how we do deploy using this system every day. So first, a little bit background about myself. I'm an engineer in DevTools team, which is a sub-team of the larger cloud engineering team. And at DevTools team, we're responsible for build and test and deploy services at Pinterest. So if you go to the internet and you do search, right, you're going to find a lot of horrible stories about the major services outages. It's just because a single software deployment. And I'm sure some of you, or maybe most of you, are fear about deploy. Certainly I do. I'm a developer, and I do a lot of code deploy, and I certainly share that fear. Yeah. So this is certainly true at Pinterest. Even with a small code change, a click of the button, millions of users get affected, hopefully in the good way. So we want to build a system really reliable and reduce the fear of the developer and promote the best deploy practice, enable them to go fast and safe. This is very critical to our success. And deploy, turns out, is a very hard problem to solve as well. At Pinterest, we have tens of thousands of machines, and the machines get scaled up and down every day. And we have hundreds of services. The services get updated every day. So how do you to keep track of all those hosts and the services up to date is indeed a very hard problem to solve. And the list goes on, right? We want to support all the services internally at Pinterest, written in different programming languages. That's a challenge. We want to keep zero downtime. Just because we are deploying doesn't mean we're going to get Pinner get affected negatively. And we want to support one-click rollback. And it has to be one click, right? Because in the middle of a crisis and panic, and you want to reduce the complexity as much as possible. And we want to support hotfix. Sometime when a rollback either is very costly or simply not possible. We want to make sure this hotfix process is very smooth. And we want to encourage developers to do staging, right? They want to stage their changes first, do more integration tests before they push to the production. And the developer won't do it unless you give them a very, very simple, easy process to use. We want to support auto-deploy. If it's done right, it's going to improve the developer velocity in a great way. And we want to support different deploy model. And then the list just goes on and on. So with that, let me introduce Teletron. And that is the internal deploy system we created at Pinterest, which is going to support all the features I described in previous slides. It has been in production for a year now, more than a year, and it deploy some 300 services at Pinterest. It managed tens of thousands of hosts, and it have about 1,000 deploys per day. And in case you are curious, Tian-Ying is actually a name after a character in Transformer. It's a supercomputer that can do a lot of cool things. Yeah. And this is an overview of what the Tian-Ying dashboard looks like. So I'm going to zoom in on some of the details. And for example, on the left, we pack a lot of most used actions on this left panel. For example, on the top, create deploy. Click the button, you're going to see all the available code changes since the last time. And also, Tian-Ying gave you a lot of more details of all the code changes. For example, it's going to tell you who did it, when it's been done, and for what purposes. So basically, you know exactly what code changes you're going to deploy. And next is a rollback. So one click, you roll back to previous state. Technically, not one click, two click, because you have to get confirm your action. Yeah. Otherwise, it's too easy, right? Yeah. And we have promote, hotfix. I'm not going to go to more details. But on the right-hand side, you notice there's two deploy stage. There's canary and there's production. It turns out it's very typical. This is a very typical Pinterest service setup, and we find this is very effective. So moving along, on the top, it's some of the highly configurable metrics that is actually relevant to your service. You get the real-time feedback while you are doing the deployment. It's like driving a car, right? And you get all the real-time information, and you have all the controls on your ridge. And then in the middle, right, this is the status of the current deploy. From the left, so first it's a build, right? It's deploying a version of your service from the master branch, and it turns out to be a rollback deploy. And the state is succeeding. Even though it's 100% done, right, we are still calling it succeeding. It's because, again, we are living in cloud. Machine can scale up and down anytime. So even though right now it's succeeding, it could be, turns out some machine have some troubles, and we want to know about it. It has been going on for 4 hours, and has been accepted, meaning it has passed your integration test. And yeah, and that's start by me. So on the right, there's some interesting actions I want to talk about. On the far right, there's a button called the restart. If you click on that, it's gonna actually restart your whole cluster with exactly the same version of software. It's come handy. And there's on the left is a pause button. Some developers find it's very useful, especially at the beginning of your deploy, right? You find something is wrong, or maybe not wrong. You want to verify something at the last minute. You can pause and then resume. And on the left, we have a show commits, which is going to tell you all the new commits introduced by this particular deploy since the last time. Cool. Next, I'm going to talk a little about the license we learned from implement Tian-Ying. First, keep the design simple. You want to decouple a lot of your external dependencies from your core logic. Tian-Ying in its core is a very simple and classic 3-tier client-server architecture. In the middle is a Tian-Ying service itself. It's a RESTful service, and it's going to serve the dashboard in the front end. It's also serve command line, and also serve deploy agents, which is a simple Python script runs on all your hosts. We're going to talk about that a little bit more on the next slide. And you notice on the bottom line, right, and there's a lot of different systems. So Telegram actually interact with all those systems. For example, the Jenkins, right? So every job in Jenkins, the last step is actually calling Telegram through the RESTful APIs, and that's how Telegram get to notify all the available builds to deploy. Also, Telegram talk to Slack or HipChat upon any state change of your deploy. And at Pinterest, our engineer just log out at the chat room, and it's just very convenient. Telegram also talk to either Fabricator or GitHub. That's why Telegram can tell you who do the commit and when and what. But the important thing I wanted to notice is that all those components is external to Telegram, that you can turn off any of the components and Telegram will still work just fine. That's how we separate the core logic with the rest of the external dependencies. So next, I want to talk about a little bit about this push versus a pull system. So when you design a large distributed system such as Telegram, most likely the first question you're going to ask yourself is, are we going to use push model or pull model? So for those of you are not familiar with those terms, push model is like your copy file from one system, one computer to other computers. But the server pushes the data onto the clients. On the other hand, the pull model is like your browser updates itself, right? It's going to pull the data from the server on its own. Now, when you design a system working with thousands of machines, right, chances are some of the machines will be offline because of network partition, because some temporary failure on the hosts. So to keep track all of those different cases, timeouts and retries, and it's just so hard, right? But the pull model actually is a very elegant model, and because the client can take care of itself. And so the deploy agents we have is actually using the pull model. It's going to talk to the server periodically. It's getting instructions, execute them, and then report the status back. And next, there's a very important decision that we made that I want to tell you that may actually make our life very easy. And that is, the deploy agent cannot make any important decisions on their own. Every step is supervised by the server. And this not only make the agent code super easy and robust, because remember all the deploy agents are going to run all the servers, right? You want to keep them change minimum. And also it gives the server a lot more control over the clients. If you remember the pause button we have, that's because the server says nobody can do any deploy, and that's what happens. And last, I want to talk about a little bit about how we solve the problem that for the internal Pinterest services. They're written in different programming languages. How do we support that model? We accomplish that by treating service code as a black box. So we don't want to know exactly what your service do, but every service is going to provide us a list of scripts, and we call them deploy scripts. And Telegram doesn't care what the script do, and we just call them at the right time. But you can guess from some of the names, for example, pre-restart, right? And usually you want to do is you want to drain your traffic, deregister yourself from the service discovery, and just prepare yourself to be shutting down. For example, in the post-restart, right? You want to warming up your cache. You want to run some smoke test, and finally register yourself back to the service discovery to be receive the traffic. So finally, what's in the future? We love to support containers. It's just going to open up a lot of opportunities for us to try different cool things like faster rollback and different deploy model. And it also allows us to use our computing resource more efficiently. And we're going to open source Tidyshot at the end of this year. So for any one of you interested, you can check the engineering blog we have for any incoming announcement. Or you can talk to me directly if you have any questions. And with that, thank you very much. I'm going to give my podium to Jeremy. Thank you.
All right. Can you hear me? Okay, good. Oh, let's go this way. Oh, green button? There we go. Okay, well, the good news is everyone gets free deployment software in December. So just to introduce myself, my name is Jeremy Carroll, and I'm a site reliability engineer here at Pinterest. And what I do today is talk to you a little bit about concepts of how we run databases in the public cloud. If I was going to explain the details in depth of how all of these systems work, we'd be here all night, and I want people to go home. So in general, I'm going to talk about high-level concepts and some of the ways that we think about how we scale and design survivable systems in the cloud environment. And if you look at the background, so if you're not aware, Pinterest is a visual bookmarking tool to go find the best things on the internet and then save them into collections called boards so you can do them later in real life. So if you see, actually, I've been pinning a lot of stuff about motorcycles, about a bike that I'm building. So it's kind of important. We're talking about databases that I can make sure that all the things that I saved will be there so I can do them later in real life. That's important. So philosophy. So in general, when we talk about building databases in the public cloud, I kind of saved a collection on a board of some really cool software hardware I used to have in the past when I was in a co-location facility. So really cool stuff. So if you look, I have some Cisco Nexus 7000 switches, real expensive purpose-built hardware. And if you look at all that hardware, there's a lot of stuff in common with all of them. They got 2 of everything. You see, they got 2 power supplies. They got a bunch of different blades. I bet you I could probably just try to trash that system as much as possible, and it'll still keep going. The reason being is the strategy in that type of environment is that you want to avoid failure. So all of these things have manuals that have descriptions about mean time between failures. So how many hours can this thing run before it fails? And you're buying this purpose-built expensive machines so that it can stay up and running. But one thing is that when we're on top of the public cloud, we don't have access to any of this. So we really can't avoid failure whatsoever, nor would we want to. So instead, we actually choose to have reliable and resilient software built on top of, and I put it there purposely, commodity cloud components. So if you're not aware, Pinterest runs 100% on Amazon Web Services as a cloud provider. But we don't actually use Amazon's platform offerings. So for example, if you go to Amazon today, they will actually sell and run your databases for you. They have abstractions for MySQL. They have abstractions for distributed key value stores. So they can actually provide that entire platform for you. But at Pinterest, we actually use them as an infrastructure provider. So we use their basic building blocks. We use their compute, we use their networking, and we use their storage. But we run all of our databases on top of those components. So we kind of have to make a reliable system out of those things. So how do you manage these things inside the cloud? So there is a really cool analogy that you can actually use farm, cattle management as an analogy for how you run your public infrastructure. If you've never heard about it, it's called cattle, not pets. But the basic synopsis of that is that if you treat something, in this case, a virtual instance running on the cloud or whatnot, as a pet, you have a very intimate relationship with it. You give it a name. If it gets sick, you nurse it back to health. And if you want to scale it, you make it bigger. So, it's a pet. You have a very personal attachment to them. But if you look at like maybe a homestead or a cattle ranch, they have no attachment to other animals. They basically don't give them any names. They put an ear tag on them with just a label. And if they get sick, let's just say they don't nurse them back to health. And if you want to, get a bigger ranch or whatever, you get more cattle. You scale that way. You just get more of them. Now, when most people talk about that, they're talking about stateless services. So things that don't hold data. But I'm here to tell you at Pinterest, we actually treat our databases in this way. we kind of come up with ways to operate and manage all of our databases that hold real pinner data, example being my motorcycle board, on that type of system. And we kind of have a test that we kind of just do, like a little tiny test, to see if you're actually treating your databases like pets or not cattle, is that if you can go to one of your engineers that's running some of your storage and ask them a simple question, like, for example, who is the primary instance or virtual machine running, shard 28? And if they know the name off the top of their head, most likely it's a pet. And most likely it's probably hard-coded in code somewhere, and then somebody's going to do a code ploy, and it's just not very dynamic if they know that information. So here at Pinterest, we actually have all of our databases just have GUIDs. So it's really hard to kind of know that information. But we have to do tools and services to make it easy for us to support those. So one thing is that how do you do that? So if all your databases are GUIDs, and how do you do that? Well, in general, as an engineer here, you don't directly talk to databases or storage. So if you have a product or service that you want to launch, you're going to talk to a service. So one thing that we have a kind of philosophy that if you have shared state, that belongs in a shared service. So if you want to save pinner data, which we call our users, you're going to talk to a service. So for example, some of the storage systems that we run here at Pinterest, we run a sharded MySQL environment, which all engineers proxy through a service to. We also support HBase as service. We've talked publicly about Zen, which is our graph abstraction on top of HBase. We also have some other systems called User Metastore, which is almost a distributed key value, kind of Dynamo-like system on top of HBase. But the important thing is that the engineers don't talk directly to talk to the service, and that you have to use service discovery to do that. So we're in the public cloud, and we have all these random machines come with GUIDs. You have to have a way to find them. And we use Zookeeper as a system that we've custom built around, so that all these things, when they come up, register, and other people can find them. We've done some talks about service discovery, but in a nutshell, you have to have a way to register yourself as a provider of a service, a way to look up that service, and a way to connect to that service. So that's a very important kit technology that we need so that we don't need code deploys to actually change your routing environment. In addition to that, all the databases themselves will save their shard mapping and where their location is inside of Zookeeper. So if we have a failure of our database, we can just go update that map and have our tools and everyone reflect that so that we have dynamicism within that. And in a cloud environment, that's very important. The next thing when I talk to people about how we manage our databases that kind of gets a little bit of a rise is that all of our database storage is on ephemeral disks. So if you are not aware, on Amazon, they have different types of storage. They have a storage called Elastic Block Store, which is basically a network-attached storage device. And if you choose to use that, the nice thing is that you decouple the instance or virtual machine from crashing from that data being available. So that means that that instance goes down, your data is still safe. Now, at Pinterest, all of our database is stored on the ephemeral disk, which means it's the local storage that comes with the instance. So if that instance dies, the data goes with it. And we couple their fates together. And the important thing is that we use all these solid-state instances on Amazon, which they provide local SSD state, and we have all of that. So basically, if we powered off a machine, all the data goes down with it. The important thing is that we have to ensure reliability of the system through highly replicated copies of this data in geographic locations, and that's the game we kind of play. And my Tian-Ying will talk about that very shortly. So next thing is that we have failure. We're in the public cloud. But when users actually use the service and they pin something, so for example, if they're on the internet and they see the pin it button and they pin it and they want to save it to their board for later, we have some tricks about perceived latency and availability by making almost all of our website asynchronous by design. So that means when you pin something, you'll tell our system that, hey, I pinned this, and it will enqueue it in a distributed system called pin later, which is a queuing system that will do that action later, because there's a lot of things that need to happen on the back end when you pin something to the databases. So for example, we'll go ahead and resize the images. We'll find the board that you pinned it to, maybe put the thumbnail of your last image on the board. We'll do a lot of things where recommendations and all these things. But we don't want to do that synchronously and make the user wait. But instead, we'll actually tell them it was done, and we'll do it later. So for example, we'll fan out that pin to all your users, all the people that follow, and that takes time. But the reason why I'm talking about that is we're talking about databases, is that's kind of a key component to us being available. So it will decouple the write availability of our database shard system from the read availability. So for example, if we have a database failure and it goes down, let's say, just to make it easy, numbers have 100 shards, and one goes down, then that would normally mean that 1/100th of all my users can't use the service. But in this type of system where we have multiple copies of the data, I can maybe just do the reads from the system that's still online, and I can queue all those writes for later. So I can say, you know what, we're going to get to that, and they don't know the difference. Basically, the system that I described has at least once delivery semantics. So the way that we do our system allows us to decouple that availability. It's kind of a cool technique. But that's kind of my general high-level spiel about architecture, and I just want to invite my colleague Tian-Ying to talk about how we design for failure in the cloud. Thanks.
Hi, hello, everyone. So my name is Tian-Ying, and I'm a software engineer in the storage and the caching team. So tonight, I'm just going to talk about design for failures. So cloud. So failures will happen, especially probably in the cloud environment, you probably have more. So here's a list of failures I'm going to talk about tonight. So you can see that they're listed from most likely happening to the least likely happening. But you can see that the impact is also getting bigger as you go down the list. So how do we handle all those failures? So we basically have different strategies for different failures. But in one high-level sentence summary, basically we replicate data within and also across data centers. So now let's first zoom into the data center, which is also vivid zone in the Amazon's terminologies. So just as Jeremy just mentioned, so we use the ephemeral disk. So when the instance is gone, the data is gone. Therefore, all the data in our system are replicated. For instance, the HBase will always have replication factor of 3. So any data, you will have 3 copies that's sitting in 3 different instances. However, Amazon places multiple virtual instances on the same host. And the physical host is actually a black box to us. You have no control about the mapping between the physical host and the virtual instance. So what does that mean? So this means that when Amazon terminating a physical host, it is likely that all the 3 copies you had sitting on the same host, and then data is lost. So how can we handle this kind of failures? Well, in high level, the goal is you want to try to place a replica across multiple physical machines. Now, how to do it? Well, the simplest thing I can tell you is you can use the highest number instance type in the family so that you have only 1 or maybe at most 2 instances in the data center, in the physical host. Well, there's some other ways that you can achieve this goal without using this highest number instance type. But I'm not going to talk about here. If you want to know more, you can talk to us, offline time. And so that's within the data center. And then now let's zoom out to the high level again. So basically, we also replicate data across the data centers. So for instance, in our company, most HBase clusters are operated as a pair, which means you have 2 HBase clusters sitting in 2 different data centers, and they're replicating data to each other, which is called master-master replication. So you can write to any of the clusters, and they actually replicate to the other side. So both sides has a full copy. And of course, the replication is very important. The quality, the lagging behind. So we do make sure that replication is working great, and we monitor it carefully. Otherwise, we cannot talk about any of the benefit we're going to use in the next. So with this system in place, then we can do lots of things with this architecture. First, whenever there's availability zone failures, whether it's the whole data center power outage, or maybe just have a corrupted data within that cluster, you can just easily fail over to the other cluster. There's no damage caused. And then there's another situation is the data center is actually healthy in general. However, sometimes you see that some instances just behave badly for some reasons. Turned out to be, we have seen is there's like network connectivity issue between some nodes, like lasting for 7 minutes. We see this socket timeout, lots of errors in the HBase log, like lasting for just keep going, keep retry, and then 3 minutes later, everything is okay. We also see some weird case that, the instance behave bad, and eventually turned out to be there's somebody else virtual instance actually placed on the same host as us, and then at certain time of day they start to run some job and then start impacting us. So with all those things happens, you don't really want to fail over to the other cluster quickly. Instead, we choose to use the speculative execution, which is you speculatively issue the same request to the other cluster when certain threshold exceed. And then we'll wait, and whichever the cluster that return result back first, we're going to use that result. It's because we have the good replication we can trust. And then also, Pinterest is online serving service. However, we do have offline job we need to handle. If without this kind of architecture, the offline job, will be shared in the same cluster as online job, and it will impact each other, inevitably. Or you can just add more capacity to, meet their peak time. But with this, we can just always run the offline job in another cluster, separate without impacting each other. And the last is easy maintenance. As you know, humans make mistakes. You probably don't want to run any change on the online-facing clusters, right? It's risky. And again, with this structure, we always run the maintenance on the slave cluster, and so don't have to worry about bringing down the Pinterest. Okay, now the recovery system. So earlier I mentioned that when you have a region failure, which actually means all the data center in the whole region are gone. Normally this will be like some natural disaster, cause the whole East region power outage or something like that. So the question is, when that kind of disaster happens, how can we make sure Pinterest can actually go back online as fast as we can? So with that goal in mind, that we come up with a recovery system. So now we have this recovery system, and we actually can bring back the HBase cluster, which is actually used to power your home feed pings and all the other services. We can actually bring back the HBase cluster with all the data within hours. The reason we can do this fast is because our recovery system is not just a backup system as most other recovery systems. We focus a lot on the rebuild and recover. So because this feature is so easy to use, turned out to be we have been using this actually regularly in our day-to-day operation life. So for example, it's been used very often to bring do the data center migration. And we have also been using to set up some testing environment with the same copy of the production data to test some bugs or some features. And also, we also use often for recovering a corrupted data center, corrupted cluster that's actually caused by human errors. So, of course, the recovery system also take care of the backup. So our recovery system actually do regular backup the data to the Amazon S3 services. And we do have the checksum, everything in place to make sure that, the transferring everything, is not corrupted. So as you can see, whenever the disaster happens, we can just use the same recovery system and then bring back the system. We know that it will work, and we know it will work well because we have been using it often. So with this system in hand, we feel much better. We don't worry about the region failures, or we don't worry about human error caused data corruption. So we can sleep better at night. Okay, so that's all I'm going to talk about tonight. And if you want to know more, you can visit our engineer blog, or we also given tech talks in different conferences. You can check those out. Or even better, if you're already here, you can just come to talk with us. Okay, so let's pass by. Thank you.
Thank you, Tian-Ying. Well, I hope you've been enjoying the evening. I'm the last speaker, the bookend, if you will. I'm going to share with you a little bit some of the lessons from Pinterest cloud journey, a little bit at a higher level. I think you got hopefully a lot of depth from the speakers today about how we manage the cloud. So to start off, let me share with you a little bit about just the infrastructure scale to just get some context. So front end of our service, we take something around 150,000 requests per second, which comprise about 50 billion or so pins, and roughly around 100 million plus users around the world, and about 300 or so discrete services. What that really means is tremendous amount of infrastructure growth. So in last year alone, we have doubled our compute footprint, tripled our storage, and I can tell you that the public cloud has enabled that tremendous product velocity for us. And that has been a great benefit. But let me share with you a little bit some of the lessons that we've learned along the way as we scale this massive infrastructure. So first thing I'm going to talk about is this notion that a good colleague of ours have coined here at Pinterest called operational Buddhism. We don't get attached to our servers. We know that they can go away anytime. And because we don't worry as much about the core physical infrastructure, it has heightened some of our other senses. We'll talk about some of those senses. First is, I think, a tremendous discipline around software automation and configuration management. So we use Zookeeper for application configuration. We use Puppet for server configuration. And one of our colleagues was sharing with me a couple of just days ago, it was one of the first places or environments that has been where instances and machines launch consistently and come up. And it's surprising how much taken for granted we do that. But that's been a feat that I'm pretty proud of. Next, I think because our infrastructure is ephemeral, it forces us to build resilience in software. I mean, that's kind of, yeah, okay, that's kind of heard and done, and not as much hardware as we've been talking about. What does that really mean? So for us, I'll give you an example of our search team. They launch a new index every day that powers the insights of all of our users derived from the 50 billion pins. They launch a new index every day, and they throw the old one away. You can just imagine in a traditional infrastructure that would be a little interesting to do. And there are many examples like that. I think when we run into a little bit of a error-prone host, what we found a lot more effective is to just throw away the host and just bring up a new one. So these are some of the things that we've learned along the way that has forced us to build resiliency in software because infrastructure is largely a black box. And that kind of comes into the next point where most of our infrastructure is managed from application metrics down. So we have a tremendously complex metric system that our visibility team builds. They ingest something like 750,000 metrics a second. And that's what drives a lot of our software automation. That's what drives a lot of our alerting. And I think as a result, we've been able to manage this infrastructure at quite a bit of scale. One of the last points that I want to talk about is what happens as you grow in the public cloud and the complexity grows. It's fairly easy to get going, right? It's relatively straightforward. But I'm here to share with you some learnings that we've had that as the complexity grows, these are some of the things that become relevant. Many cloud providers talk about, and it's actually very convenient for them, that capacity planning is not relevant in the public cloud because it's infinitely elastic. I'm here to tell you it is not. At the end of the day, behind that is a real data center, and you do run into physical limits, and not just for that reason, but also because if you're in an API-driven infrastructure world, it gives you a tremendous amount of velocity, and that's great. But mistakes can also be very, very expensive. I can tell you about the number of times when a cluster of hundreds of machines is left stranded for some reason because, some software made a call, sped them up, or a log job that has created petabytes of storage that nobody's using. So you have to have this discipline around capacity and efficiency to go along with an API-driven infrastructure. And we found that to be very helpful. Also, some of the building blocks are different. Some of the new nomenclature for how we manage capacity and efficiency in infrastructure are things like reserved instances, things like spot instances, on demand, and then ultimately managing services to auto-scale with demand. Now, those are the new building blocks, and a combination of those things, you tweak them right, is give you a more efficient and well-managed infrastructure in the public cloud. And last, I would encourage you to invest in infrastructure analytics. We're relatively early in that stage to figure out what our analytics story is, and it's looking pretty good, but I wish we would have started a year ago. And I think building a healthy understanding about who and what and how your infrastructure is being used would be very helpful. Let me share with you some other guidelines that have come along the way that has helped Pinterest scale. At some point, you need to have the conversation about what is the guardrail for your firm, whether it's IaaS or PaaS or all things from cloud providers. We found that to be helpful to have that discipline at Pinterest to say that we use largely IaaS. We use compute, storage, networking. That has allowed us to innovate on top with the platform layers. I think you heard from some of our friends of what they've done on the storage layer and many of the other areas. We opened open source some of our MySQL capabilities. That has allowed us to bring tremendous amount of talent to Pinterest. And at the same time, it has helped us with a good guardrail to innovate, at the same time be able to scale. But having that right discussion about what is right for your firm is important to have that discussion. Next, as the complexity grows, you need to have a conversation about supply chain leverage. What is right for your firm, whether it's one cloud provider enough that provides you everything, that dependency enough, or do you want multi-clouds or a hybrid cloud, if you will? These are important questions that we're contemplating, and I'm sure as complexity grows, many of your firms will. And lastly, a lesson that we run is around workload profiling. Oftentimes, as infrastructure sprawl grows, it's important to profile the different workloads that you need to leverage. And then public cloud providers purposely have a huge number of different type of instance types. And it's important to get one right. You want to look at whether it is compute intensive or IO intensive or memory intensive, because otherwise you can leave stranded a lot of resources that may not be helpful. So these are some of the lessons that I wanted to share with you. But here's a slide that really excites me about our challenge at Pinterest. And that is that a pin lives forever. A half-life of a pin is about 3.5 months. That is about 1,700 times longer than an average social media post. Think about that for a minute. Because we are a discovery engine, the relevance of a pin is almost perpetual. So we think from an infrastructure perspective, we have a much more harder computational burden than perhaps some of our peers. Well, we think about that as an opportunity. We think about that as an opportunity to innovate in infrastructure. And we also think that it's a great way for us to build deep science about cloud infrastructure at Pinterest. So that's all I have to share with you today. I hope you enjoyed the discussions from all the speakers. And hopefully we can continue the dialogue. And thank you for coming. And I want to thank all the speakers for their time tonight. Thanks.
You always step to my girl.